Hello, my name is Markus Lohrey, and I will talk about the subgroup membership problem in the group GL2 set. So this talk is about algorithmic group theory, and I will speak about one particularly important group theoretical decision problem, namely the so-called subgroup membership problem. So let us fix a group G and elements G1 to Gn from the group G. Then we denote with G1 to Gn in triangle brackets the subgroup of G generated by the elements G1 to Gn. And then we can define the so-called subgroup membership problem for the group G, which I denote by subgroup of G. So the input for this problem consists of group elements G, G1 to Gn. And the question is whether G belongs to the subgroup generated by G1 to Gn. Now a question which arises here is, how do we represent elements of G? If G is, for instance, a finite permutation group, then it's quite obvious. We can represent elements of the group by explicitly writing down the permutations. But if G is an infinite group, it's not so clear. Clearly, we need G to be countable in order to have a finitary representation. Now, one nice class of countable groups where we have easy or simple finitary representation are finitely generated groups. So a group G is called finitely generated if there is a finite subset sigma from the group G, a so-called generating set, such that the whole group is the subgroup generated by sigma. And in this case, we can represent elements of the group G by finite words over this alphabet consisting of all group generators and their inverses. So if we have a word over this alphabet, then it represents the group element obtained by multiplying the symbols in the word from left to right. Now the point is here that sometimes this representation of group elements by finite words is not the most natural one. So let us consider an example. Take, for instance, the group GL2 set of all 2 by 2 matrices over the integers with determinant plus minus 1. So this is a group. It's well studied in, for instance, linear algebra. And this group is well known to be finitely generated. So, for instance, these 3 matrices generate the group GL2 set. And it's, I think one can say it's folklore that the subgroup membership problem for GL2 set can be solved in polynomial time if group elements are represented by words over a fixed finite generating set. The particular generating set that you choose is not important. So if this problem is in polynomial time for one finite generating set, then the same holds for every finite generating set. Now let me briefly show you the proof of this well-known result. So first of all, GL2 set is a virtually free group. That means there is a finitely generated free subgroup F in GL2 set, such that the index of this free subgroup is finite. This is a well-known fact from algebra. And the second fact is, this was shown by Avenhaus and Madlena, that for every finitely generated free group F, the subgroup membership problem for F can be solved in polynomial time. And here we assume that group elements are given as words over some generating set of F. And the third fact that we use was shown by Grunschlag in his PhD thesis. If H is a finite index subgroup of a group G, then the subgroup membership problem for the whole group G can be reduced in polynomial time to the subgroup membership problem for H. So these two results together, they imply that the subgroup membership problem can be solved in polynomial time for any virtually free group and therefore also for GL2 set. And I say it again, here I always assume that group elements are represented by words over a finite generating set. Now, finite words are clearly not the most natural representation of elements of our group GL2 set. The natural representation are, well, we just write down matrices, 2 by 2 matrices, with, let's say, binary encoded integers. That's certainly the most natural representation of group elements. And the point now is that such matrices with binary encoded integers, well, you can transform them into finite words over a finite generating set, but this leads to an exponential blowup. Take, for instance, this matrix here, which belongs to GL2 set, and n is here a binary encoded integer. So this matrix can be written, well, it's equal to this matrix, where this matrix here, 1, 1, 0, 1, is a generator. Yeah, it belongs to our generating set from the previous slide. But now n appears here as an exponent, and n is given in binary representation. So the length of this word here is exponential in the length of the input representation of this matrix, if we represent numbers in binary notation. Nevertheless, we have the following result, and this is the main theorem, or let's say the main application of our results, namely the subgroup membership problem for the group GL2 set can be solved in polynomial time, even if group elements are represented as matrices with binary encoded integers. Before I come to the proof of this result, let me state a related theorem of Gurevich and Schupp from 2007. They considered the group PSL2 set, the projective linear group, and this group is defined as SL2 set, so this is the set of the group of 2 by 2 matrices over the integers with determinant 1. And then you take the quotient by the subgroup generated by the negative identity matrix. So it too is the identity matrix. So this means in this quotient you identify or you equate matrices A and inverse of A. They are considered to be equal in this quotient. Now this group is well known. It's also called a modular group, and it has a very simple algebraic structure. Namely, it's a free product of a cyclic group of order 2 by a cyclic group of order 3. And Gurevich and Schupp proved that a subgroup membership problem for this modular group can be solved in polynomial time when group elements are represented as matrices with binary encoded integers. Now, I will come back to this result in a moment, but let me now start to give you an overview on the proof of our main theorem. And for this, we introduce, one could say, a succinct version of the subgroup membership problem, which deals with the so-called power words. So let's fix an alphabet sigma, and then a power word over sigma is an expression W of this form. So here I have words U1 to UK. So these words are written down explicitly, symbol by symbol. And then we take powers of these words. So we have here exponents N1 to Nk. And these numbers are binary encoded. We assume them to be positive. So this is a power word, and such a power word can be seen as a succinct representation of a very long word, since the numbers N1 to Nk are given in binary encoding. The word, the length of this power word W, can be exponential in the length of the representation with binary encoded integers. Now let's come back to groups. Let me again fix a finitely generated group G, with a finite generating set sigma, and I assume here, without loss of generality, that sigma is closed under inverses, so every inverse of a generator is also a generator. This is just a technical assumption which makes some details easier. Now the power subgroup membership problem for G, called power subgroup of G, is the following problem. Again, we have group elements G, G1 to Gn. Now all these elements are given as power words over the group generators. And the question is again whether G belongs to the subgroup generated by G1 to Gn. So this is a succinct version of the subgroup membership problem where the group elements are given in a succinct way by power words. Now for the proof of our main result on GL2 set, we use two reductions. And the first reduction is based on this lemma, which goes back to this paper of Gurevich and Schupp that I've already mentioned, and the same result is also proven in this paper by Dikert and Elder. They proved the following, namely, in polynomial time, you can compute from a matrix A in GL2 set, where the entries are given as binary encoded integers. You can compute a power word over some fixed finite generating set of our group. The concrete generating set is not important. And this power word represents the matrix A. Now, by this result, it clearly suffices to prove that for every virtually free group G, the power subgroup membership problem for G can be solved in polynomial time. Remember that our group GL2 set is virtually free. And using lemma 1, then we see that if we can prove that the power subgroup membership problem for every virtually free group can be solved in polynomial time, then we know that for GL2 set with binary encoded matrix entries, we can solve the subgroup membership problem also in polynomial time. So this is our new goal. Now let me come to the second reduction, and this is based on this lemma here. Let H be a finite index subgroup of G. Then we can reduce the power subgroup membership problem for the whole group G in polynomial time to the power subgroup membership problem of H. And this result is analogous to the result of Kuhnschlag that I've mentioned a couple of slides before, but it deals with the power subgroup membership problem. So also the complexity of the power subgroup membership problem is preserved by finite group extensions. So by this lemma 3, we have now a new goal, namely, we only have to prove that if we have a free group, a finitely generated free group, I will not mention always explicitly that the groups are finitely generated, so all groups in the following will be finitely generated, then the power subgroup membership problem for our free group can be solved in polynomial time. If we, from this theorem 4, with the previous lemma, it follows that the power subgroup membership problem for every virtually free group can be also solved in polynomial time. Now, a special case of this theorem 4 was shown in the paper by Gurevich and Schupp that I've mentioned already. But they proved only a restricted, they proved a special case of this theorem 4, where they consider only power words of this form where the words that appear in the basis, they are single generators. So they belong to sigma, to the generating set. And this is, of course, a special case. This is a particular form of power words. So our theorem 4 is more general, but for Gurevich and Schupp, this is sufficient. Remember, they were only interested in this modular group. And for the modular group, the modular group has the nice structure that it is this free product of a cyclic group of order 2 and a cyclic group of order 3. And in this group, you can make similar tricks as in a free group. For us, we cannot use the result of Gurevich and Schupp. The problem is that it's not clear whether lemma 3 holds also for this restricted version of the power subgroup membership problem. So where the power word has this form here, that all base elements are single generators. Now the point is, even if we start with a power word where all base elements are single generators and we apply this polynomial time reduction here, the result will be a power word where the base elements may have length greater equal than 2. So we cannot use the result of Gurevich and Schupp. Okay, so this is now our new goal. We want to solve the power subgroup membership problem for a free group in polynomial time. And I want to show you some of the proof ideas, but let me first show you how to solve the ordinary subgroup membership problem for a free group in polynomial time, where group elements are given as words over the generating set. And the simplest algorithm for this problem is based on so-called Stalling's folding procedure. It's a very nice idea, which can be nicely visualized So let me show you the Stallings folding with an example. I consider here the free group generated by two elements, A and B. And I consider the subgroup here generated by two elements, AB A minus 1 and A B square A. And I want to know whether AB A belongs to the subgroup here. Now we start with a so-called bouquet graph. And this bouquet graph contains for each generator of our subgroup a loop which spells this generator. So for instance, here we have A, B, A minus 1, and we find it here, A, B, A minus 1. So this vertex here is a distinguished vertex. It's the so-called root vertex of the graph. And the second generator, A, B, B, A, can be found here, A, B, B, A. So we can consider this graph here also as a finite automaton where the initial state is this root vertex here, and the root vertex is also the single final state. And one important point here is that implicitly I have also inverse edges in the graph or in this automaton. So for instance, there's an A edge from this node to this node. Therefore, there is an A minus 1 labeled edge from this node to back to this node. I do not draw these inverse edges explicitly, but they are there. That means in particular that I can reverse this A minus 1 labeled edge. Let's do it. Then we get this A labeled edge. It represents the same graph, it's a so-called inverse graph. And now what Stallings did is he folds this graph. And folding means that whenever we have two edges with the same source node and the same label, we can fold the two edges together into a single edge. We can do the same also if we have two edges with the same target node and the same label, simply because the graph is an inverse graph. The inverse edges are also there. So let's do this folding. So for instance, that means we can fold these two A edges together. So that means that these two nodes here, they will be identified and we get this graph. Now we can fold again. Here we have an A edge. Here we have also an A edge. Let's fold. And we obtain this graph. Then here I have a B loop. And here I have another outgoing B edge. So that means I can fold this edge into this loop. And thereby I identify this node with this node. And the result is this graph. And then the same happens again with this outgoing B edge, and then I obtain this graph. And now I cannot fold anymore. So this graph is completely folded, and then I take the group element that I want to test for membership, A, B, A, and I simply check whether it's accepted by this finite deterministic automaton, where this root vertex here, or root node, is the initial state and also the single final state. And here the answer is of course positive. If we take the word A, B, A, it's accepted. A, B, A. An important condition here is that this word that we check for membership, it represents a group element, and this word here must be freely reduced in the free group, which means it does not contain a factor of the form A minus 1 or A minus 1A and so on. Okay, so this is Stallings folding. And now we want to deal with this power compressor, the power subgroup membership problem. And the main idea now is that we extend Stallings folding procedure for graphs where besides of the normal edges that are labeled with the generators A minus 1, B minus 1, we have also so-called big edges which are labeled with powers. And these powers, P to the N here, are of course those powers that appear in the power words that are given in the input. So P here is a word over the generators and their inverses, and it has to be reduced in a very strong sense. I will skip all the technical details here. Basically, this means that P must be freely reduced. it must also be cyclically reduced, so it should not start with, let's say, A and end with A minus 1. And P must be also, for instance, a primitive word. And then there are some other conditions which can be enforced by a preprocessing. And the number n here, the exponent, is of course a binary encoded integer. And then in the Stallings folding procedure for these, let's say, power compressed graphs, what we have to do is we have to fold edges that are labeled with a power with the same base element. So for instance, if we have those two edges in our graph, here I have p to the 5, here I have p to the 8, then what I can do is that I can fold this edge here, the shorter one, into the longer edge. And that's the result. So this node in the previous graph is now here. So I will skip many technical details here. We need also some other folding steps where we fold a path labeled with P, but consisting of edges labeled with single generators. Such a path has to be also folded into such a power edge. And we have to be careful that the whole process does not blow up the size of the graph. This can be all done. It's a little bit technical, and you can find it in the full version of the paper. So that's all I want to say about the proof of our main result. And let me conclude with some related work and also future work. So one open problem that we want to consider is the subgroup membership problem for the free group, where group elements are represented by so-called straight-line programs. So straight-line program is a context-free grammar that produces a unique word. And this problem is more difficult than the subgroup membership problem for power words, so the power subgroup membership problem, simply because a power word can be easily transformed in polynomial time into an equivalent straight-line program. So the complexity of this problem is open, but I would conjecture that it can also be solved in polynomial time. Then one could also study the so-called rational subset membership problem for a group G. I mean, this problem has been studied before. So in the rational subset membership problem, the input consists of a group element G and an automaton A with transitions labeled by elements of G. And of course, such an automaton defines in a natural way a subset of G. And then you simply ask whether G belongs to L of A, so the language of A, which is considered as a subset of the group G. And this problem was studied before for many classes of groups, and this is an interesting result in this context, proved by Bell, Hirvin-Zalo, and Potapov in 2017. They proved that the rational subset membership problem for the group PSL2 set, the modular group, with binary encoded matrix entries, of course, is NP-complete. And what is open is the complexity of the rational subset membership problem for a free group where transitions are labeled with power words or even straight-line programs. So I would conjecture that these problems are again NP-complete, but it's open. And finally, this is a famous problem which is open, I think, for a long time, is the subgroup membership problem for the group GL3 set. So the set of all 3 by 3 matrices over the integers with determinant +1 or -1. Is this problem decidable? That's also open. So that concludes my talk. Thank you very much for the attention.